Welcome back to Logic, Language and Information. In this lesson, we turn to the truth tables for the trickier connectives, the conditional and the biconditional. Here, expect to be puzzled and perplexed by the conditional connective. Many beginning logic students are, including myself about 25 years ago. As in the previous lesson, we give the truth table construction rules applied to arbitrary propositional formulas A and B. A material conditional formula, A horseshoe B, is read as if A then B or A implies B. In other courses using logic, you may see an arrow symbol rather than the horseshoe for this connective, but we'll be using the horseshoe. A formula A horseshoe B is true exactly when. In every case that A is true, then B is also true. It asserts that there is a truth-transferring direct connection from the antecedent A to the consequent B. We'll start in the fourth row of the table, when A is true and B is also true. Here, it is clear that the conditional A horseshoe B must be true here, and we write 1. This is because truth is transferred, in this case, from A to B. In the third row of the table, when A is true and B is false, it's also clear here that the conditional A horseshoe B must be false, and we write 0, because in this case we have a direct violation of truth transfer from A to B. The other two rows of the truth table cover the cases when A is false. In these cases, there is no truth in A to transfer. So we end up with the conditional A horseshoe B being true, and we write 1 in the first and second rows of the truth table. The conditional is truth transferring, but it is not falsity transferring. So when the antecedent A is false, the conditional comes out as cheaply true. Medieval logicians had a Latin phrase for this phenomena, ex falso quodlibet. From falsity, anything follows. Combining these four cases, we see that the material conditional, A horseshoe B, has the same truth table as not A and not B. It is true in all cases except for when A is true and B is false. The material conditional is the truth functional core of the implies or if-then connective in English, with the truth of the conditional expressed purely in terms of the truth or falsity of the antecedent and the consequent. In natural language, when we assert A implies B, or if A then B, we mean there is a content connection leading from A to B. To say there is a content connection from A to B is to say more than there is a truth transfer connection from A to B. For example, if the content of propositions A and B are about the occurrence of events, then when we say A implies B, we usually mean that there is a causal connection leading from A to B. The classical two-valued logic we are using in this course does not allow us to include this sort of content connection in the semantics of the conditional. So it does not exactly capture the semantics of natural language. One needs to move to non-classical logics with richer semantics in order to capture a content connection leading from A to B. Nevertheless, this classical truth functional material conditional is, as we use here, is the conditional actually used in practice in application areas of logic, in mathematics and in all its applications in science and engineering, in philosophy, in linguistics, and in computer science. The classical semantics of the material conditional can lead to some unintended consequences. For example, formulas of the form if P then, if Q then P, are always true in every row of the truth table. Now let P be I am a penguin, and let Q be Elvis is dead. Then the following sentence is always true. If I am a penguin, then if Elvis is dead, then I am a penguin. Yes, it does seem a bit strange. In the next lesson, formulas such as this that are always true, as in the table here, will be classified as tautologies. Before proceeding, make sure you're comfortable with the truth table construction in this example. At level 0, we've copied the truth value columns under the atomic propositions for each occurrence of P and then of Q. At the first level, we've evaluated the conditional in blue to get the column which is only false in the second row when Q is true and P is false. And finally, at the second level of evaluation, we complete the column under the main connective where the antecedent is P and the consequent is the blue column for Q horseshoe P. There are no truth values that give a true antecedent and a false consequent, so the outer conditional is always true. Now it's time to get some practice. Consider two ways in which negation can be combined with the conditional connective. And let's compare the formula if P then not Q with the formula not if P then Q. Complete the truth table. And remember, start with the atomic propositions where you just copy the truth table column under each occurrence of P and likewise for Q. How did you go? From the solution here, we can see that there is a clear difference in semantics between the formula if P then not Q and the other formula not if P then Q. When P is false in the first two rows of the truth table, the difference is clear. The first formula, if P then not Q, will come out as true in this case, whilst the second formula comes out as false on the first two rows. On the other hand, when P is true in the last two rows of the table, we see that the two formulas have the same truth value. 1 then 0 and 1 then 0. If you have more questions or comments, take a look first at the course notes and then head into the discussion board to follow things up. The biconditional is the bidirectional version of the unidirectional material conditional. We read the tribar symbol as if and only if. Again, let A and B be arbitrary propositional formulas. A biconditional formula, A if and only if B, is true precisely when A and B have exactly the same truth value. On the first row, when A and B are both false, the biconditional A if and only if B must be true. And likewise, on the last row, where A and B are both true, the biconditional must be true. The biconditional is false precisely when A and B have different truth values. On the second row, A is false and B is true. And on the third row, A is true and B is false. Let's get some practice straight away, and in the process, make sense of the claim that the biconditional is the bidirectional two-way version of the unidirectional one-way material conditional. let A and B be arbitrary formulas, and then consider A if and only if B and how it compares with the conjunction formula. If A then B and if B then A. How did you go? Let's quickly review the solution. In the column under the horseshoe symbol within A horseshoe B, we get the pattern 1, 1, 0, 1. Whilst in the column under the horseshoe symbol in B horseshoe A, we get the pattern 1, 0, 1, 1. By taking the conjunction, we end up with the column 1, 0, 0, 1, which is exactly the same as A if and only if B. So, A if and only if B as a formula is logically equivalent to the conjunction. If A then B and if B then A, where we will formalise this notion of logical equivalence in a lesson ahead. What this also means is that we can define the biconditional in terms of the conditional and conjunction. If you have more questions or comments, then take a look at the course notes and head into the discussion boards to follow things up. This brings us to the end of the formal semantic definitions for the connectives using truth tables. In the next lesson, we'll put truth tables to use by introducing a number of different useful classifications for formulas, the notions of being a tautology, being a contradiction, being satisfiable, and being contingent.